Okay, welcome to the first of our video recorded lectures for this week. This one is on the topic of bit operations. This topic will be ultimately of most use probably to those of you who are going to be computer engineering students, but also for a lot of you who are going to be doing networking types of things. These are tools that are used a lot in those, and some of the computer scientists may use them as well. The bit operations are really something that gets us either close to the hardware. In other words, we're dealing with single bits of a multi-bit value, or we may be also doing some sort of encryption or decryption, or some very sophisticated math where we need to manipulate things in sizes that aren't the normal sizes. So we'll see some examples of these as we go through these topics. So the first is when we look at some of the data types that we're used to and that we learned about in 1030, we know that the integer data type in particular is, as well as long, are machine dependent. In other words, on the 32-bit machine they may be one size, on a 64-bit machine they may be another, maybe 2 bytes or 4 bytes. So although Bitwise applications work well on these integer types, there are often cases where we need to know for sure how big a value is regardless of what architecture we're on, so that we're more machine dependent. So we can create integer data types of specific sizes as well, so we have a little bit more control over exactly what's there. So here's some examples of those that we might create. We can have signed values or unsigned values, and notice the name is appropriate. So we can have an 8-bit, a 16-bit, a 32-bit, or a 64-bit integer. Obviously the 64-bit ones would only be on the appropriate operating system. And sometimes that's important for us to know, especially if we're going to work with bitwise operators, because we want to pick out a particular bit or a group of bits to operate on. We have to know how many are there total so that we can do that. And if it changes, then the positioning that we do may be off. So this is something that C provides. There are a couple of operators that we can use. There's an AND operator, which is similar to the logical AND that we use in if statements and things like that, but it has more of a mathematical meaning. It uses sort of the same symbol. It uses the single ampersand, whereas in the logical operations we use the double ampersand. Or similarly, we can use, and it uses the singular vertical bar, whereas we use the double vertical bar for the logical OR operation. One that we don't have in the logical types of operations is something called the exclusive OR, and we'll see exactly what it does in just a minute. It's a variant of the OR, and it's represented by the caret, or sometimes called the hat operator. And then we have the NOT operation, which in the logical world we use the exclamation point. In the bitwise world we use the tilde, or sometimes called the squiggle, operator for those. We also have some shift operations, which actually shift the bit pattern either to the right or the left, which has some mathematical interpretations as well, as we'll see in a minute. And for those, we use the angle brackets, or the less than, greater than symbols. And for left shift, we use 2 less than signs, and for right shift, we use 2 greater than signs. You'll see they form an arrow pointing either to the left or to the right, so it's pretty easy to figure out which one's which when you see it in an expression. So let's look at some code that uses a couple of these. The first 2 lines of code there just create a couple of variables. A short int, and we're going to assume for purposes of this that that's a 16-bit, so it'd be on a 32-bit machine. And a short unsigned int, one called s, one called u. First thing it does is it sets s equal to -1, which, if you see there in the comments, that would be represented by an FFFF. We haven't talked about machine representations yet, but when you take a value like 1, for example, let me bring up like a little notepad. So if we take a value like 1, and let's just represent it as 4 bits, well, as 4 hex bits. Let's say it's an 8-bit quantity. So 1, 2, 3, 4, 5, 6, 7, 8. That would be the value 1. in binary. To get the negative of that, and the way we represent negative numbers in computer architecture, if you will, is by something called the 2's complement. And you can create the 2's complement through a set of steps. The first step is to create the 1's complement. And we do that by simply flipping all the bits. So by flipping, obviously a 0 will become a 1, so it'll be 1, 1, 1, 1, and then 1, 1, 1, 0. That's called the 1's complement, and that's step 1 of 2. And then we create the 2's complement. So here we flipped the bits. And the 2's complement, we accomplish this by adding 1 to the 1's complement. So in the number above, that if we added 1 to that, we'd end up with 1, 1, 1, 1. That didn't change. And these two didn't change, and we add a 1 to the 0, we get a 1. So that would be the value for -1. And in computer architecture in 2610, you'll learn more about why that's done and then how that's used in mathematical operations. So that's what this FFF is out here. Of course, these are hexadecimal numbers, and F is a 1111. It's a value of 15. Okay, then we're setting U equal to 100, and that's what its hexadecimal value would be, 0064. And then we're ORing it with 0x0110. Okay, so now remember, in hex, each of these 4 digits represents 4 bits. So if we look at hex 0010, let's look at the value here. So we started out with 0x0064. So that'd be 0000, 0000, and then 6 would be 0, 4, 6, and then 4 would be, so that's what it look like in binary. The 2 zeros are obvious. This is the value for 6, and this is the value for 4. And then if we take the number that was shown for the AND operation here, which was, or operation, which was 0100, that would look like this, 0000, and then 0001, and then 0000, 0000. If we were to OR those, ORing means that we look at the matching bit patterns between the value and what we're going to come to call the mask, or this value that we're ORing with. And 2 zeros is a 0 in an OR, because neither one is true. The idea here is it's true if either one is true. So anywhere there's a 1 and a 0, we'll end up with a 1. Anytime there's a 1 and 1, we'll end up with a 1. Anytime when there's a 0 and a 0, we'll end up with a 0. So if we were to get the result, we get 0000, 0001, because there's a 1 there. And then we get 0, oops, sorry about that. And then we get 0110, and then 0100. Which, if we turn that into hex, the first digit's a 0, the next digit's a 1, the next is a 6, and the final value is a 4. So we get 0164, which is the answer that we see here on the slide. So we've ORed those together. Now, what the effect this has, if we assume for a minute that this first pattern, the value that we started with, were a bunch of switches, okay? And each 0 means the switch is off, and 1 means the switch is on. And then we ORed it with this pattern. What we've done is we've taken a switch that was off, if you will, and turned it on. And of course, if it was on, it would have left it on too. So this mask basically says, turn this switch on if it's not already on. And if it is already on, leave it on. And the zeros in the pattern mean leave it the way it was, don't change it. So a 1 means change it if it's the opposite, and a 0 means no change when we use an OR. Now let's see what happens if we use an AND. So in this line 6 down here, we're saying S ANDed with 0xFFF0. And S right now is FFFF. So let's see what happens with that one. So if we had FFFF, that's easy to write down because that's all 1s. And then we're going to AND it with FFF0. So First three are just ones. And the last one's all zeros. Now an AND, if you remember for logical AND, for an AND to be true or 1, both values have to be 1. If either of the values is 0, we get a 0. So the first block is all 1s, the second block is all 1s, the third block is all 1s, but the last block is all 0s because in the mask, the second value, they were all 0s. So we can see the AND has the effect of we put a 1 in the position of the mask, that says essentially leave it unchanged. In other words, if it was off, it'll stay off because if this was a 0, we'd end up with a 0, 1, which would be a 0. If it's on, leave it on. But the zeros force something to be turned off. In other words, in all those positions, if these were switches, those last 4 switches that were on would now be turned off. So 0 forces a turn off with an AND, whereas 1 forces a turn on with an OR if it's not already on. Okay? Now let's talk about exclusive OR for a minute. Okay? An exclusive OR is very similar to OR. OR says if either value is 1, the result is a 1. And if both values are 1, the result is a 1. If both values are 0, the result stays a 0. In the case of exclusive OR, it just changes one of the rules. It says if both values are a 1, then make it a 0. In other words, they have to be exclusive. They have to be different. So if either one is a 0, if we have a 0, 1 pattern in either direction, we get a 1. Of course, a 0 and a 0 would still be a 0. But if we have two 1s, it converts back to 0. So you think of this as a toggle. It basically says for any position in the mask for an exclusive OR that you put a 1, it's going to toggle that position either off or on. If it's off, it's going to turn it on. If it's on, it's going to turn it off. So we'll just basically change the position. So if we look at S exclusively ORed with U, so we know S was all 1s. So right now everything's on. And now we're going to exclusively go that with a U, which U was 0, 1, 0, 0. So that's all zeros. And then somehow I got off there a little bit. I guess just because the zeros are bigger. And then 0, 0, 0, 0. So everywhere there's zeros, there's no change. So there's no change there. The next block, there's no change for the first 3. But now we have a 1 and a 1, so it's going to turn that one off. And then the rest of them are no change. So we turned that 1 off because it was currently on by putting a 1 in the mask. Said if it's on, turn it off. Okay. So that's what we accomplished there. And the last two on this page are the shifts. So U shifted 3 times. That means basically shift all the bits to the left, and we're going to shift in zeros on the right-hand side. So if we took U, and U was currently, what? U is the 0x00, oh, no, it's not. It's 0164, because we did that OR. So if we take the 0164, so that's 0, and then 1, and then 6, and then 4. So if we're going to shift that to the left 3 times, it basically means the first time, so the first shift, we'd get rid of the first 0, we'd shift the next 3, and then we get a 0 from the previous bit. And then that 0 is gone, so we get 0, 0, 1, and then 0 from the previous bit. And then we get 1, 1, 0, and then 0 from the previous bit. And then we get 1, 0, 0, and shift in a 0. That's one shift. Next shift, we got 3 zeros left, and then we pick up a 0. We have 0, 1, 0 left, and we pick up a 1. We have 1, 0, 0 left, and we pick up a 1. And then we have 0, 0, 0 left, and we pick up a 0. And then the last shift, we have 0, 0, 0 left, and we pick up a 0. We have 1, 0, 1 left, and pick up a 1. We have 0, 0, 1 left, and we pick up a 0, and 0, 0, 0, 0. And if we did that right, we should end up with the final answer, which the first is a 0, and then 1, 0, 1, 1 is 8, 10, 11. And that's a B in hex. Okay. And then the next one is in the 2 position, and then a 0. So we did it right. Okay. So we end up with 0B20 hex. Now, that also has a mathematical interpretation, and that is every time we shift to the left, it's like multiplying by 2. So if we knew what the decimal number was for you originally, this would be like multiplying by 2, by 2, by 2, so multiplying by 8, if you will. And so that would be whatever the original value was multiplied by 8. And then, of course, the other shift is exactly the same in terms of shifting to the right is like dividing by 2. So if we shift it twice, that'd be like dividing by 4, 2 squared. And here's just another example similar to the one that we just did. And left shift and right shift. Now, the ones complement operator, we saw how to do a ones complement in the notes that I had over here a minute ago. That's just flipping the bit, and that's what this tilde does. So it would accomplish that ones complement, and then we just do a +1 to accomplish that. So if we want to take the twos complement a number sort of in C, we could say, if we had some value B and we wanted its twos complement, we could say A equal tilde B +1, and that would accomplish taking the twos complement, because this would do the ones complement and then the +1, so A would be the twos complement, which is ultimately the same as saying A equal negative B. That's what the twos complement is. It's the negative representation. And please don't confuse these with the logical operators. We've certainly used these with if tests mostly, but also whiles and do whiles, and maybe even in a for loop or two. These are logical. These have to do with the whole value when we AND two things together. Are they both true? So true is anything non-zero. So if we had two numbers and we were ANDing them together, if they're both non-zero, then the result would be true, and etc. And so we have logical not, which is the logical meaning of true or false, not the same as a mathematical negation, if you will. So we use these in statements like this. We use the double equal sign, etc., etc. So these will go in if tests or for tests or whatever. And they're not the same thing. That's why this is in here, just re-emphasizing they're not the same thing. Okay? So we use bitwise operators in C for the same reason they're used in assembly language, which you'll learn more about in 2610. They let us manipulate individual bits. We can do things like fast multiplication and division. And in fact, a lot of our compilers, what we call optimizing compilers, will convert your multiplication and division code when it's a power of 2 to be a shift. So if you did like x star equal 2, it would convert that into being a shift because you're multiplying by 2. So it would shift to the left one time because the shifts are faster. Multiplication is actually an algorithm and it has multiple steps in it. So it takes several CPU cycles, whereas a shift is an elemental operator, which means it just takes one CPU cycle or one cycle to accomplish that operation. So we gain performance by doing that. And optimizing compilers are ones that just recognize those kinds of things in your code and change them so that even though you didn't write them that way, that's how they operate. Now sometimes that can get you in trouble if it optimizes out stuff that you didn't want to do, but you can turn that off in the compiler, and in future classes you'll learn how to do that. So here's an example of somewhere where we use these in Linux or Unix for that matter. There's the chmod function. And the chmod function, there's several ways you can use it. What chmod does is it changes the permissions for a file. So this first argument is a file name. And you can do it with octal numbers, because for every file in Linux, as you learned earlier, there's 3 permissions. There's the owner permission, the group permission for anybody who's in your same group, and then there's an other or world. And each one of those is represented by an octal number, which is really 3 bits, 0, 1. And so for example, bring this back over here. For example, 777 would say the owner permission is 111, which means read, write, and execute. That's what those. This is read, write, and execute. So I'm giving myself permission to read, write, and execute. Okay. So that's really what I'm doing there. and I could say group permission might be read and execute. So that'd be a 5. So I'm giving read and execute. And I might give the world only permission to execute, which would be a 1. So that would be a permission of 7, 5, 5, 1. Okay? So you can do it that way with chmod, and you can put that number in there, and it will change the permissions of the file of that. But you can also do it, this is showing it using some constants that are declared that I can basically accomplish the same thing by ORing a bunch of stuff together. So this is saying SIRUSR says the user can read, and then the W1 says the user can write, and then this one says the group with IR, so the group can read. So this would be giving read and write privileges, or a 6 to the owner, and read privileges to the group, which would be a 4. So this is like a 640. I'm not giving any privileges to the others, or the world, if you will. So we can use these to create that set of bits, settings for the permissions, instead of doing it in octal, as I did on the notes page. Okay. So we can modify some of the permissions. We can also use something called the stats function and do large groups or change other permissions as well. So what stats does is uses a structure where we fill in the values in the structure and then pass that to chmod, and we can change it that way as well. So that's another way to do it. Okay, the next topic in here is something that many of you may never encounter. It's not as big an issue as it used to be. This quit being as big an issue once Apple quit using the Motorola PowerPC chips and switched over to the Intel chips. But there are still a few machines out there, especially some mainframes and mini mainframes and office level servers that use some other chipsets. And of course, in the embedded processor world, this can still be an issue too. So you computer engineers need to know some of this. And that is, internally in the computer, we're representing numbers that are more than 1 byte, so 8 bits. What order are the bytes in? In other words, if we look at a 4-byte value, for example, is the byte that's leftmost the highest order byte, or is it the lowest order byte? In other words, are things written from left to right or right to left? And in the days when several different architectures still use the PowerPC, and then the others use the Intel, and Intel clones like AMD, this was an issue because they did it differently. So notice it's called Big and Little Endian, but Endian is not spelled with an I, it's an E. It has to do with the end. In other words, is the beginning byte the big end or the little end? So it has to do with the order of the bytes, not the bits, but the bytes themselves. So Big Endian is the most straightforward. That means the leftmost byte stores the largest part of the number, and then etc. on down to the last byte. That's kind of the left to right, the way we're used to reading. Little Endian is the opposite order, and Intel uses Little Endian representation. So if you actually look at the way things are stored on disk or in memory, they actually use a Little Endian implementation, whereas the PowerPC, the stuff that Apple used to use, and a lot of other processors use Big Endian. So of course we've settled on using the one that uses the least straightforward method, but that's an editorial comment. So I can determine Endianness with code. If I create an unsigned short and put a value in there, and then create an unsigned character and look at a particular value, I can look at the first byte or the first character, which is 8 bits. And if it's a 12, in other words, the 1, 2, then it's a Big Endian machine. Otherwise, it's a Little Endian machine. In other words, if I looked at this hex number, if my first byte had those 2 characters as a hex value, then that's the big end. In other words, that's the most significant part of the number. If it was a 3-4, actually it'd be a 4-3 basically, because it'd be backwards. Then it would be a Little Endian machine, but I'm just checking for the Big Endian. That's the easy way to do it. So I could write a little piece of code to check and see if it's a Big Endian or a Little Endian. And that makes a difference when we're, for example, transferring numbers from one machine to another, and we're doing it in binary or as a number. That's why when we talk about file I/O, I said that a lot of times all files are written as ASCII files. In other words, all the numbers are written out as the characters that represent their individual digits, like 1, 2, 3, 4, as opposed to the 4-byte quantity 1,234. Because if it's ASCII, everything's 1 byte, and so order doesn't matter, and I can read the ASCII on any machine. Whereas if we write binary files where the values are actually written out as numbers, they take up less space, but if I happen to transfer that data file to another machine, and it happens to be the opposite Endianness of the machine that it was written on, and if I don't know that, then the numbers aren't going to be right. And so I'm going to basically read the file as garbage. So that's why this is important. And back in the day, I ran into some of these problems, not knowing about Endianness initially, and so it created a lot of bloody forehead disease for me. So when do we care? Normally we don't. If we're doing everything on the same CPU or same kinds of CPUs, it's not a problem. When we transfer between different computer systems, that's a problem. We can solve that easily by using ASCII data, but then we have to translate it as we read it in and write it out. Another place where this becomes an issue is in networking, and when we're transferring things between machines. So what they did in the networking world to sort of solve this problem is create something called the network byte order. In other words, over the network, when you transfer something over the network, it's assumed that everything is big Endian. In other words, that's the default for the network. When you walk in the room, you're big Endian. So in the TCP/IP stack of steps that it goes through to translate something to prepare to send it over the network and wrap headers around it and all that kind of stuff, and create network packages, and then on the other end to strip all that off and eventually get just to the data. We call it the stack, if you will, the TCP/IP stack. There's functions within there that let me convert from big Endian to little Endian and vice versa, but it's called network byte order. So we basically convert from host to network order, or from network order to host order. That's what these two functions are. Now, in the networking code today, that's all done for you. So this is at a very low level. So only if we're writing really low level code, like in embedded systems where we're doing direct control of the packets on the network, then this would become an issue. So most of this is sort of behind the scenes for most of you. But it is going on. And so if something is not in network byte order, it has to be converted to network byte order before we ship it out over the network so that everybody can talk. That's why even 10, 12 years ago when Macs were PowerPC, a Mac could still talk to a Windows machine on a network and talk to printers and all those other kinds of things, because everyone basically agreed that when you're on the network, this is the way it is. So kind of like when you're in a certain country, the default language is the language of that country. And this is just really showing at the level of machine language, this is some assembly language code, how we could accomplish that. And then here's a little C function that would accomplish reversing the order the same way. We're just basically taking the unsigned int, the 4 bytes, and this is almost the same thing as using a union. In fact, we could do this with a union. We're using this value, but then representing it as an array of characters so that we can swap the individual bytes around their order. You see 3 is going into 0, 2 into 1, 1 into 2, and then 0 into 3. So we're just reversing the individual bytes but by treating them as character or 8-bit single byte quantities. Okay, and the last part talks a little about counting bits. So for example, if I had some data coming in and I wanted to count how many bits were on or off or whatever, I could do that, and here's some C code that would do that. So if I get an unsigned integer in, let's just assume we're on a 32-bit machine, so that'd be a 4-byte value. So initialize our counter, and then while the data is not equal to 0, we do data ANDed with data minus 1. So if this is the data value, we don't care what the first few digits are. If we do a minus 1, which one we're subtracting, we have to do all the borrows and carries. So it would look like this. When we AND those two together, then we could tell if it was a 1 or a 0. So we would count the number of bits that were there. So we'd count the number of bits that were on, for example. So that's one method. Another method is to use a lookup table, and so this goes through that. So we initialize the counting bits. So there's using the first method. And here, basically by converting the individual values to bytes, we could count how many bits were on there. We could actually add the 1s and 0s together and this sum would equal the number of ones in the data. So and there's an example of doing that here. And this may or may not be something you need to do. This would be interesting if for example, we're shipping ones and zeros out over like a serial line, and so we wanted to see how many of the bits were on versus how many of the bits were off, or count the total number of bits we were sending, those individual ones and zeros. Because we're talking about serial communication, that's really what we're talking about. There's the cable, even though it has multiple strands, some of them are used for handshaking, in other words, for coordinating our discussion. And only one of those lines is used for data, and so it's based on the timing sequence. It's either a high or a low. In other words, it's either on or off. And then after a certain amount of time goes by, we read the next on or off as the next bit value, etc. But there's only one line that actually has data on it, one wire, if you will, that actually has data on it. So these are just some examples of doing those. And there's the code that would implement that shifting method. I don't really expect you to know about counting bits, just know that it exists. And those are very common techniques, and that's one of the things that you could, if you needed to use it in a job, it's certainly not going to be on a test. You need to use it in a job, you can certainly look up one of those techniques and determine which is the best to fit your needs. Okay, so that ends the first lecture. I know I said originally there were going to be 2 video lectures. I'm actually going to break it up into 3 parts, so each one's a different topic, but they cover the topics for the week, because there's really 3 topics this week. So this one's a little over 30 minutes long, and the others will probably be about the same. So you can look at each one by topic. That way, if you want to come back and refer to them later, then you can look at just the topic you want and don't have to go through a really long video to find the part that you want. So this one was on bit manipulation and bit operations in C. And then stay tuned for the next 2. Hope you guys are having a good week and you were able to get through homework 1 okay, and you started working on homework 2. I will be in the office on Thursday morning until about noon before I have to go over to the South Campus or main campus. If you need to see me, you can come by. And then I'll be briefly in the office Friday afternoon after I come back from the event over on the South Campus or main campus. I won't be in the office Monday through Wednesday. Actually, I will be in briefly Wednesday afternoon, but I'll be at an orientation, new student orientation. So, but you can certainly email me Monday and Tuesday and the first half of Wednesday, as well as Sunday. I will be able to receive email. I will only be able to receive and answer it on my phone, so I won't be able to do lots of code-related things. You can certainly send me stuff and I can look at it, but I won't be able to go try anything or do any of that kind of stuff. So your best bet there is to go see one of either the TA or the grader, or interact with them via email if there's something specific where you're having compiling issues or something, because I won't have access to those tools. I'll be out in the wilderness, so, but not so far out in the wilderness that I won't have cell phone reception, so I will be able to check emails and such. All right, thank you very much, and stay tuned for the other